started. So welcome to our webinar series for the month of June. We're really happy to have you, especially in this high vacation season. And so we would just like to thank you in advance for giving us a few minutes of your time. Today we're going to be taking a look at what I call a love-hate relationship between pigments and dispersants. They each need each other, but they both don't like each other at the same time. So it makes it a difficult challenge for formulators to create their best dispersion. So with that, we'll go ahead and get started. I am recording the session so that all of the attendees will get a link to the recording as well as the presentation. And if you have any questions, please feel free to use the chat box and I'll address them at the end. And if that's not your thing, go ahead and reach out to me directly with your question and I'll try to answer it. So we'll go ahead and get started. So obviously Sudarshan is a pigment manufacturing company, not a dispersant company. However, we work very closely with a lot of dispersant manufacturers to understand how our pigments interact with dispersants and other additives. So some of the information that I'm sharing with you today, I've just taken from their websites, and especially with PIC and Lubrizol, BSF, Evonik, and Colorant are some of the main ones that we work directly with. Also, a lot of this information comes from my many years of experience working in the coatings field prior to coming to Sudarshan, and so a lot of this information hits home with me. As far as pigments, of course, all pigments, both inorganic and organic, need some sort of additive to the formulation to be able to disperse it as well as stabilize it in the final formulation. And so each of these types of chemistries brings its own unique set of challenges to work with respect to choosing the appropriate dispersant or surfactant for that particular formulation. And so we're going to go through each of the application areas and talk about some examples of what we've done in the past, so that it might give you some clues as to where to turn to with your formulation needs. So we've talked about this before. As far as being a pigment manufacturer, we manufacture pigments for all three areas: pigments or plastics, coatings, and inks, as well as the additives that are out there. They are also typically developed for specific applications and formulations within those applications. So on the pigment side, I like to say for plastics, we like to develop plastics that are what I call clean, in terms of there's little to none of surface treatments or other additives in there. The pigment particles themselves are softer and smaller in size for improved dispersion, polymer dispersion. The residence time in a plastics application is very short, so we want to make sure that we prepare the pigment ahead of time for the most optimal dispersion that we can get in that short residence time. Coatings and inks are very similar in that they both have very wide and complex portfolio of formulation types within each of these applications. Because of that, the pigment portfolio that is created to support these areas are also quite complex and varied. You've got water solvent, you've got automotive decorative, you've got sheet fed and UV inks. So there's a lot of different areas where pigments need to go for those applications. So when you look at a portfolio of pigments by application, you're going to see a lot more options for products in both of these areas versus, say, a plastics area. which is a little bit more simpler in terms of formulation types. So we've talked about this in the past, where the first key area with respect to pigments and dispersants is in the chemistry of the pigment. About 75% of the performance from that pigment comes from the actual chemistry. And this is also going to dictate the need of the dispersant in your formulation. The remaining 25% or so is really geared towards what finishing types are placed upon that particular pigment product. And that's going to also sway the dispersant choice for optimal dispersion. And we'll go through a little bit of that later on in the presentation with some examples. Next important fact about pigments in terms of dispersants is the actual crystal shape. The shape, or in particular the aspect ratio of these, will dictate a little bit more about where what need that particular pigment will have for a dispersant. You can imagine a needle-like pigment particle, which is going to have a higher surface area. It's going to require maybe more or potentially more complicated dispersion to be able to get a optimal dispersion versus something like a sphere, cube, or block, which has a very small aspect ratio. Along the same lines as the actual crystal itself, the shape itself becomes the actual particles that you might see. So the crystals, of course, are called the primary particles. These are never going to be achieved in any dispersion process, and they are very short-lived in the reactor itself once those crystals are formed. What usually happens is once those crystals are formed, they tend to come together in smaller numbers in a very tight bound aggregate to create the actual pigmentation. It is this aggregate that we try to achieve in the dispersion process. The aggregate size can be quite varied, and it is the process of the dispersion and formulation that is key to getting to that smallest aggregate size. And lastly, what you see in the bag of pigment is the agglomerates. These are very loosely bound clusters of the aggregates that you start with. And it is the job of the dispersion process to, one, break down these agglomerates into smaller agglomerates, and then the dispersion process itself begins to break those down further, closer to the smallest aggregate size. So the finishing steps that I spoke of, and we've reviewed these in the past webinar series. The first area is in the surface treatments and additives. So once the crystals are developed in the reactor, this is the opportunity to use those additives and surface treatments for a number of different reasons. They can stop the crystal growth at a specific point so that we create the appropriate size that we're looking for. They can also be used for impeding some of that aggregate growth that I spoke about. Once the pigmentation is complete, there's a lot of options for drying, and depending on the end application required, we have our choices of a variety of drying processes that result in different hardnesses and particle size as well. The next option we have is in the milling area, where we can reduce the particle size even further. We can also shorten the particle size distribution as well. Again, depending on the end application area, our choices of pulverization equipment to use is varied. And lastly, each and every batch that is created is then blended into that final lot. And there's another opportunity to add additional additives before it is bagged. Additives could be rosin, it could be clay, or in some cases it might be blank fix, depending on the end application. there are three basic steps of the dispersion process, and I'm not telling anything that you don't already know, just pointing out a few key areas. The first step is the wetting. This is the first opportunity that your formulation sees that those agglomerates from the bag of pigment. The next step is the grinding process, where these agglomerates are then broken down to those smallest aggregate sizes. Once they're ground down, they need to be stabilized so that they don't come back together and you have a nice stable dispersion that you can use in your final formulation. So taking a look at the first step of wetting. Wetting is really just a replacement of those micro air bubbles at the surfaces of the pigment with the liquid that surrounds them. So it's a key area for preparing the premix of that dispersion so that it is in the best quality shape before it hits the dispersion process. So I'm a very visual person, and I know a lot of you are on the call are as well. So I've taken a video from the BIC website, and I highly encourage you to take a look at their website. They have some very very interesting videos to go along with their information. So this video is a phthalocyanine blue that is placed in water. So first you're going to see the pigment from the bag, the agglomerates, hitting that water surface. And with no wetting additive, you can see that it just sits on top and doesn't do anything. But once that wetting additive comes in, you can start to see and envision how those micro air bubbles are being replaced by the liquid as the pigment particles start to fall down into the liquid and prepare the solution to be in a good shape prior to the dispersion process. The second step in the grinding area, here we are taking those that premix that we've just wetted out and prepared. We're taking those agglomerates that are already started to be broken down by the wetting additive. Now we're going to start to break those down even further into those agglomerates. So what we see is the pigment out of the bag. We saw that in the video earlier, coming in, and that is the poorest state of dispersion, basically. And so the combination of the physical dispersion process and good mixing of the formulation, which contains a liquid medium along with other additives like the wetting agent that we just saw, maybe some additional dispersants. And what we want to do is we want to separate those particles into the smallest that we can and keep them apart from each other via the dispersant additive. That's where the stabilization comes into play. And once we've done all that work and imparted all that energy and time into creating those small particles, we need to make sure that they stay small and they stay away from each other so that they're stable in the formulation. Again, I've taken a short video from the BIC website with a visual of a good dispersion and a poor dispersion. So the first thing that we're going to see is the poor dispersion, where there's no dispersant aid in there, and the pigment particles start to come back together and form very large flocks. What this results in is very poor tint strength and stability. This part of the video is showing that same dispersion with some dispersing additives, and all those small particles that were created are stable and stay away from each other, creating that nice dispersion. When we talk about dispersants, we need to talk about a little bit about the chemistry of the dispersants. So the key in dispersant areas is there is an A section which absorbs to the pigment surface. So pigment is the A section, and then the B section has affinity to the medium that it's in. whether it's a solvent or a resin solution. The B section is the one that likes doesn't like the pigment, but likes the medium, and those arms then keep the individual particles away from each other. There's a lot of polymers out there that are used as dispersants. Here's a nice depiction of the different types of polymers. So single chain polymers can have two different types, where the first type, which is the number B up there, is there's a terminal group on one end that happens to like the pigment surface. So it attaches onto the pigment surface and those tails stick out into the medium. The other type is where there's two ends that are functional on each end, kind of like a jump rope, where the handles stick to the pigment surface and the rope itself extends out into the medium. The next form, which is also a little bit to the next level of complexity, is what's called a block copolymer. These are built with two sections, an A section and a B section that I described before. The first one is a BAB, where there's two tails that stick out into the medium, and the A section, which likes the pigment, sticks onto the pigment surface. The ABA is where the section that likes the pigment are on either end of the B section, again, sort of like a jump rope, where the A sections stick to the pigment, covering it quite well, and that B section, looking like a jump rope, sticks out into the medium. Similarly, when there's two sections of two polymer types within it, we can have more of a random copolymer, where along that chain there are different lengths of the A and the B section. Again, the A section will stick to the pigment surface, where the B sections will extend out into the medium. The more complex or structured type of copolymer is typically called a comb, where the backbone is the A section, and along that backbone there are some tails coming off of it of the B section that stick out into the medium. So how do you use dispersants with pigments? A good starting point that I've always used in my career and seems to work out well as a good starting place is to take the pigment surface area, divide that by 4, and that's going to be the amount of active surfactant or additive that needs to be added based on the pigment weight. And then from there, ladder studies are recommended, where you go a little bit above and a little bit below to start to find that sweet spot for that particular pigment. As an example of some starting places for different chemistries of pigments, I brought here a number of different types of chemistries to get a feel for what's required. So 2 examples of a pigment yellow 110, both an opaque and a transparent version, where the surface areas are quite different. And that then, as the formula dictates, the opaque version with a smaller surface area is going to require less of the active dispersant than the transparent version. Violet 19, of the ones that I've included in this table, has the highest surface area, so it's going to require the largest amount of dispersant on pigment weight solids. And then conversely, the pigment yellow 138 has the smallest surface area of the chemistries that I have, so it's going to require a lot less. And then the red 122, green 7, and pigment blue 15-3, they fall in between all of these. And just a quick look at the pigment yellow 110 examples that I had in the previous chart. Here you can see the differences in the particle shape, where the transparent version is very needle-like. It's very long and very thin, thus the higher surface area and higher aspect ratio, requiring more dispersant versus the more shorter tubular opaque version. So colorants are always going to provide a visual stimulation. They're going to attract your consumer, they're going to deliver your message, and they're going to enhance your brand. So we as pigment manufacturers, we want to make sure that you get the most out of your pigment to get the most out of your end result. So selecting a pigment is a long process, and there's a lot of things to consider. Obviously, the first is your color and effect. How transparent or opaque do you need that colorant to be? Are you going to be using an effect pigment along with it? What kind of application do you need for this particular colorant? The resin system is very key in terms of the pigment as well as the dispersants or additives that are going to be in there. Thus, the concern to make sure that we take a look at interactions within that formulation of both all of the additives as well as the pigment. And then depending on what your application is, whether or not you need light and weather fastness. And that is also true with additives as well. Your application will also dictate what kind of compliance that you need in terms of a lot of different properties, but food, toy, and medical are typically key in some areas. So depending on your need, this is one thing to consider. Cost and value is always there. It's always present. But in both a pigment case as well as an additive case, you may choose a higher dollar per pound product if it gives you some additional technical properties that you can't get with another property. So again, it's also going to be, the choice is there, considering all of the things that you need to develop into your process. And then the last area, of course, is performance. And there's a long list of performance areas to consider as far as choosing your pigment and your additive of choice. And it's always going to be a balance. This is something I've always mentioned in each of these webinars. There is nothing that's going to give you 100% of all of your must-wants and nice-to-haves. But if we can move as many as we can into that musts and wants category, that's where we come in to help from the pigment side. And we can also help from the dispersant side. As I said, we've worked with all of these dispersant suppliers in the past, and we have a good relationship with them. Some examples to give you a feel for what dispersants can and can't do. The first example that I have is in a coatings area where we took a look at a particular Pigment Blue 15-2 in a solvent-based polyurethane coating formulation. And our objective here was really to evaluate the dispersant chemistry and its effectiveness for this particular pigment. And we wanted to compare it to our basic control formulation that we use at Sudarshan in this type of formulation, which is the Disperbic 161. In this case, we wanted to keep the formulation the same, so the pigment level was maintained, and the dispersion to pigment ratio was also maintained, so that we were looking at the chemistry of the dispersant itself and nothing more. So the dispersant of Disperbic 161 is a block copolymer. We also added a couple of high molecular weight copolymers, so some of those random ones. And the Disperbic 2200 is touted to be a very good one for phthalo pigments. We also took a look at a structured polymer as well. And in all cases, we also looked at using a synergist as well as the individual dispersants by themselves. Just to give you a feel, going back to that description of the polymer types, the Disperbic 161 is a block copolymer, so it's either going to be the BAB type or the ABA type, and I can't tell which, but it's definitely a block copolymer, so it's going to function in one of these two ways. The Disperbic and the Disperbic 2200 and the BicJet 9152 are both random copolymers, so they're going to look something like this. Whereas the BicJet 9131 is a structured copolymer. So most likely, the more popular in structured is this cone type of structure. So we took a look at a number of different parameters with this. So you can see here we're taking a look first at viscosity. The first thing that we saw for this particular Pigment Blue 15.2 was the addition of the synergist lowers the viscosity with every dispersant that we looked at. Some more than others, but they were all lowered with the addition of the synergist. When we look at dispersants alone, the BICJET 9152 was the lowest in viscosity. And overall, for this particular property, both the Disperbic 2200 and the BICJET 9152 with the synergist provided the lowest viscosity of all of the formulations that we took a look at. The next property we looked at was the transparency. And in this particular case, the Disperbic 2200 in combination with the synergist provided the highest transparency. Property was color development. And so for a Pigment Blue 15.2, we want to develop the most blue and the most red in terms of its color development. That's the direction of these alpha phthalocyanate pigments need to go. So what we saw here is both the BICJET 9152 alone and in combination with the synergist provided that the most red in color. And in strength development, again, we saw that in all cases, the synergist helped with increasing the strength in there. So you get more bang for your buck, if you will, with this particular pigment by use of a synergist. And then as far as individual ones, we had the best response from the 9152, 9131 in combination with the synergist. So overall, with all of these properties taken into consideration, we chose the combination of the 9152 and synergist to be the pigment of choice, or the dispersion of choice for this particular chemistry pigment and finishing pigment. Next, I wanted to take a look at, since when we talked earlier that 75% of the performance comes from the chemistry and the remaining comes from the finishing steps, I wanted to see how this dispersant formulation worked with other chemistries in the phthalo chemistry class. And so what ends up happening in that particular case is here we're focusing on the effect of the finishing steps. As I mentioned before, there are a number of areas where finishing takes place, and this is also true with phthalos. So each of these will tend to be a little different in terms of its physical properties of the pigment powder. And so we wanted to understand if we took the same, the optimal dispersant pair with that we found with the Pigment Blue 15.2 and added it to the other phthalos and to see what the results were. So on the left-hand side is the results from the Pigment Blue 15.2, which showed us that the BICJET 9152 and synergist provided the lowest viscosity. And then on the right-hand side is the Pigment Blue 15.1. For this particular product, the result was the same. The BICJET combination with synergist also provided the lowest viscosity, although the difference between the three options wasn't that great. A little difference in this particular case where the individual 9152, which was the second best for the Pigment Blue 15.1 or 15.2, now shows that it has some higher viscosity with respect to the 15.1. Moving on to the Pigment Blue 15.3, this is a beta blue. We see something very interesting here. With the 15.2, this alpha blue, the combination 9152 and synergist was the lowest viscosity, as we stated before. However, it is the highest in viscosity with this beta blue 15.3. In addition, the control that we're using, the Disperbic 161, is the same result as this combination of BigJet 9152 and Synergist. So we don't necessarily need to get more complex with the dispersants for this Pigment Blue 15.3. So it is very, very interesting here to note. The other interesting thing to note here is that whereas the 9152 in combination with Synergist was the best for the Pigment Blue 15.1 and one of the worst for the 15.3, the BigJet 9152 alone is very good for this Pigment Blue 15.3. So again, in this particular case, what it tells us is a Synergist in this particular case is not to our advantage with a Beta Blue 15.3. And finally, the fourth blue in the CPC area is the Pigment Blue 15.4. In this particular case, what we see here is our control, our Disperbic 161, again, does not look any different than the best candidate with the 15.2, similarly to the other Beta Blue here, and that the Disperbic 9152 alone wasn't a whole lot different, but a little bit worse in terms of viscosity. And lastly, the last chemistry in phthalocyanate grouping is Pigment Green 7. And what we see here is this resembles very similarly to the results of the 15.1 in the blue side, where the combination of Disperbic or BigJet 9152 and Synergist was also the lowest, and the individual 9152 was also the highest. So these two pigments perform very similarly. Moving on to in inks, I brought a couple of examples here as well. And in this particular case, we're taking a look at some UV ink information details here, where in the first example I have is a Pigment Red 146, again in a UV ink formulation, where we're taking a look at a number of different types of dispersants from a number of suppliers in this particular example. The first thing that we noticed here in this particular evaluation study was that they all created an initial dispersion, some a little bit better than others in terms of the particle size development. However, only one remained stable with time. So we only had one out of all of those examples where that it was a stable dispersion with these two Pigment Red 146 pigments. Example is a Pigment Yellow 131. I'm sorry, Pigment Yellow 13. And again, this is also a UV ink formulation, and we're taking a look at a variety of dispersants as well. In this particular case, they all performed okay in terms of viscosity. They were all somewhat stable over time with this particular property. However, there's not a whole lot of difference between each of these, although the Disperbic 168 does appear to be the better performing one of all of these. So, but this particular property doesn't really have a huge signal. However, the coloristic data does start to begin to show some additional knobs to turn in terms of technical parameters that you might be looking for, where we start to see differences in strength development as well as in the opacity or transparency development. And a quick turn to plastics. Again, we wanted to, as a pigment manufacturer, we try to create a fairly clean and soft, smaller sized pigment particle for plastic application. So the information I have for you, I've brought this from the CAD Retech presentation by Colorant last year, where they went through and took a look at filter pressure values in a number of polymers with different types of additives. And I'll share that with you today. So in the first polymer, we take a look at the pigment or PA6 polymer, and we start to see that with this pigment blue 15.3 pigment, there is a wide variety of responses in the FPV values within this particular polymer, depending on the additive that's used. Then if we switched over to PET as the polymer for the same pigment blue 15.3, we start to see where there is very little difference between the additives used in this particular study. And finally, in a PLA polymer, we start to see where, again, there's some variability or some differences between the additives used versus the neat PLA on the left-hand side in here. So it really depends on the polymer that was being used. So in short, as we all can attest to, each polymer, whether that be a polymer in plastics, in coatings, or in inks, it's got to have a unique dispersion depending on the pigment that's used, as well as the additives that are added into that formulation. So it's going to be that balance that we've always talked about to get the most out of the pigment that you are using. Reminder of Sudarshan's portfolio. We have our high performance pigments in our Sudaperm brand. We have our CICPs in our Sudatherm brand. Our inkjet are in the Sudajet brand name, and our classical pigments fall into the Sudacolor and Sudafast brand names. So we are here to help. I'm just one part of the North American team, but we are all here to provide guidance and information for you. So you can reach out to any one of us and we'd be happy to help. So next up, we're going to shift even a little bit further out, where I'm going to walk you through the Colorant R&D process and how we develop a pigment. That's going to be held in July. So take a look for that invitation sometime in the prior week. And then in the future series in August, we will take a look at another application-specific topic where we're taking a look at the impact of finishing on plastics. So stay tuned for that. So with that, I would like to thank you for your time for today, and I'd like to open it up for any questions that you might have.